Hi everybody. Okay, hopefully we are live now. YouTube says we are. This is Miss A coming to you this afternoon on May 19th, 2020. It is, oh God, what is today? A Tuesday, I think. Yeah, otherwise, why would I be streaming programming? It is very hard to keep track of the days, isn't it? Like, it's super hard. Um, you know, it's not a bad day outside. The weather's okay. There's some birds. I don't know. Could be sunnier. How's it? How are you doing out there? Hopefully somebody watches this at some point. Whenever you're watching this, how are you? Hopefully you are well. Hopefully you can go outside. A little quarantine humor for you folks. Okay. So today I am just gonna tackle one lesson here on CodeHS, lesson 1.9, because it is a little bit of a bigger topic than lesson 1.8 was, or like what lesson 1.7, right? Those ones were very, very simple. So, okay, so here we are on CodeHS, and going to programming with Karel in the student view. So this will look like what you actually see. So programming with Karel, we have gone over quite a few topics already. It's kind of amazing how quickly you end up accumulating a lot of these very early but very fundamental tools for programming. It's just like most of programming is learning how to do bigger and more complex things with these very basic kind of structures. So, for loops. This is a big one. So when we think of, when I teach programming, I am very big on thinking about the differences between the ways that human beings think, how computers think. And, sorry, computer issues. So again, how different types of brains think, human versus machine. People hate repetition. Just look at this quarantine that we're in right now, or look back at the quarantine, hopefully if you're watching this at a later date. If you think about the quarantine, right, we started hating our repetition so quickly. We do not like doing the same thing over and over again. There's a reason why factory work is, understandably seen as very tiring and full of drudgery. Working any kind of retail job kind of sucks because of how much sort of mindless mechanical repetition you end up having, right? People can get into that, right? You can get into a zone, your body can feel like a machine. But that's when really your body has kind of understood exactly what the task is, and it's just in this flow of let's do the same thing over and over and over again. But that's an exceptional way of being for a person, right? Most of us don't get into that kind of zone, and when we do, we don't tend to do it very often. But, some people it's a little bit easier, a little harder to others. Computers, though, that is utterly natural. This is exactly how they like to think. A computer would love it if you made a program that literally just sent it the same thing over and over and over again, right? You could have a computer, it would be the simplest computer in the world if you only made it do one thing, but it will do it like a machine. It'll do it repeatedly, it'll do it precisely, it'll do it the same way every time. A lot of engineering goes in to making these machines to make that true, right? You do not want a computer that when you tell it to do the same thing twice, it's not going to do it exactly the same way. People do that, but you can also talk to people. You can tell somebody they made a mistake. You can hold somebody accountable. You can yell at a person. You can yell at a computer, but it only does you so much good. But really, it's just excellent at doing a set of instructions over and over again, exactly the same way every time. And as computer programmers, I think it's really important to get into this mindset where you are really trying to work with the machine and work with the way that it thinks, like training a dog, right? You're not going to get very far training a dog if you just pretend that it's a human being, right? There are certain ways that dogs learn. And when you get into that mindset, right, when you start thinking more about what motivates this dog and what kind of buttons to push with it, it gets a lot easier. Same thing with a computer. It would be great, be kind of scary if we could just like tell it what we wanted in plain English and it could do it as far as writing programs. But, you know, for the most part, it is... Ugh, God, no. See, now I'm thinking about that. That would be really creepy. Like, ask it like, hey, how about, you know, developing this new thing for yourself today? And the computer's like, okay. Kind of a weird Black Mirror episode. But anyway, so the idea is when you're writing a program, you really want to think, or you want to kind of write it in a way that it's going to play to the computer's strengths. And the biggest thing that you can do with that is by breaking things into repeatable parts. And that's where something like we've already seen this with functions, right? That's one way to break down a problem into repeatable parts. You sort of take this action or activity that gets done over and over and over again. You make it into a function. So now you can call it repeatedly, very simply. For loops are going to now kind of take this to the next level, right? Now we're going to be able to specify, you know, now we don't have to like actually call the function 100 times if, say, we want to make Karel do like 25 backflips. We don't have to do 100 left turns. Or right turns, right? If we wrote a right turn function, call it 100 times, for loops are going to take a lot of that work out. And when we're talking computers, sometimes you might actually end up having them repeat things very, 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 very frequently. Let's say you have a big table of data and you want to do something with that data. So what you might do is you might write a loop that does something to each row. Maybe reads the row and writes it to something else. But you have to do that. Let's say, you know, this is COVID data, like public health data, somewhere like New York City. Do you have any idea how many rows there are in those tables? It's huge. I can speak personally to looking at a lot of Department of Education data. There are 1.1 million students in the Department of Education. There are like tens of thousands of schools and facilities. Like, it is an enormous system. All the tables of data are massive. So chances are, as a programmer, you're not going to want to write some kind of, you know, the same kind of function, right? You can, you know, make something call a function like take row, but you're still going to have to call take row like 100 times. You're not going to want to do that by hand. That is tedious. That is not something that human beings like to do. Most of us. Most of the time. So that's where for loops are going to come in, right? This is a structure that really plays to the strengths of doing things with a computer, right? Writing something to take advantage of loops, maybe not the same way you would want to do it again for people. People like variety. People like a little bit of variation in what they're doing. Computers don't, right? Computers are really make it very simple to repeat. So let's dive in. Once again, thanks so much to CodeHS for having, you know, such a great service, having such a great curriculum here for folks to use. I am a big fan. You know, I wish I was back at school, actually, you know, working with my students on this one-on-one. But here we are. So let's get back. I clicked on the wrong one. Sorry, my mouse has actually been acting up a little bit recently. Like, I'm thinking of buying a new one. I've got this like old, cheap, like Microsoft one that I bought maybe 4 or 5 years ago at this point. I don't even remember. It's like mostly good, but it keeps misclicking. Or like it's acting like a double click when I'm not actually double clicking. Okay. So, for loops. Right, like I said, this is the same kind of example as what I was talking about in terms of having a table of data. Now, instead of, rows of data, we have tennis balls. So what happens if we want to put down 100 tennis balls? Well, you're going to have to write it over and over and over and over again. And so the for loop is what lets us do this. You're going to learn about another type of loop eventually, and that is going to be an open-ended loop. Like there's no predetermined number of times that other loop is going to run. A for loop, the number of times it's going to run is done in advance, right? Either it's something that you, the programmer, put in saying like, I want to do this 100 times, or say you might have your program calculate how many times it's going to need to run and use that number. But either way, there is some number that's established before the loop runs, before those repeated actions start, because you don't want to just tell the computer, well, start repeating, I'll tell you when to stop later, right? A for loop is about once the computer decides to enter this loop, it knows how many times it's going to run. So fixed numbers of times. Yeah, see, this is what I'm talking about with my mouse. You see how it like clicked over like 3 slides? That was kind of weird. So for loops look really ugly in JavaScript. In the other language I teach, Python, they can be nicer in their own way, depending on how you want to like teach people about it. And there's sort of like new ways to write for loops in newer versions of JavaScript. This is the tried and true, old, just traditional kind of way of doing it. We're going to start with this word, right, for. So you're designating, for is like the keyword that JavaScript understands. And then we're going to, starting with this parentheses over here, all the way to this parentheses over here, we're going to kind of specify what this loop should look like. And the way at its basic that we're going to think about a for loop is there is some kind of counter that's stored in what's called a variable. That's where this word var comes in. So you're creating some counting variable. So there's something called I that's going to act like a counter for us, right? So every time we, do one repetition, that counter is going to go up. And then we do it again, counter is going to go up again. Or it can go down, right? We can start at, say, 100 and work our way down. Typically, I think going up is, I guess, more traditional. I don't know very specifically whether it is somehow better to go up rather than down, but I do think that like addition is sort of consistent addition is easier or I think faster for the computer to handle. But hey, if anybody is actually watching this and knows any better, please, leave a comment. I'd be interested to know. So we're going to start by declaring this counter. We're going to say, okay, I'm going to make this counter, and just by tradition, it's very traditional to just call this I, but, different people can use different, different names for this counting variable I. And typically what happens is, say, if you're running more than one loop, let's say you have another loop happening inside this loop, For that one, say we might use J, and then if we add another one, we might use K. That is also pretty traditional, right? Start at I for the first one, then go J, K, L, M, N, and up. But again, this could be a lot of things. Then we kind of specify how the counter should tell the loop when to stop. And typically, like the most typical example is we're going to have some predetermined number. That's where this like count is. That is usually something we're going to replace with a number. And this is going to specify how many times. So if I want the loop to run 10 times, that number, it's going to be I less than 10. If it's 100 times, it'll be I less than 100. So basically, right, the counter usually starts at 0. That's kind of a quirk of computers. They do like, it's usually better to start counting at 0. Then we're going to start at 0 and go 1, 2, 3, 4, 5. Count up and up and up. And then what's going to happen is, so here's what we do. Say we want to count to 10. And, okay, I think this looks like left on the stream, I believe. Okay. So we're basically going to start 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So basically, like when the computer has counted to 9, that's really how it is counted to 10 because, right, think about it, I went through all of these. Just the only difference is instead of starting at 1, I started at 0, so everything kind of got pushed. And so what basically happens here is the computer's thinking, is 0 less than 10? Oh yeah, cool, let me keep going. 1 less than 10? Sure. Is 2 less than 10? 3, 4, 5, 6, 7, 8, 9. Is 9 less than 10? Cool. Now it asks, is 10 less than 10? And it's going to stop. So that 11th repetition doesn't happen. So that's why we use less than and not like less than or equal to. So basically we want this to go from 0 to 9. And that's kind of how we will make it repeat 10 times. It takes a little getting used to, but it's also not like the worst thing to get used to in the world either. So here we go. And the I++, okay, I++, this is basically saying take the counter, ++ means add 1 to it. So this will take us from 0 to 1 to 2 to 3 to 4 and up and up and up. So basically, right, here's your counter and where you want it to start. Here's the condition that tells you when the loop should keep going. And then this is telling you what to do to the counter in between repetitions of the loop. This doesn't have to be ++. If we want to go down, we would write -. If we wanted to count by 2s, we would have a way to do that. So I'm going to, when we get to the example, I will show you a little bit of what that looks like. Okay. So in this example, there's going to be a repeated move. So by looking at this, can we guess how many times it's going to move? Well, the counter, that's I. It's going to start at 0, because, right, we start with this counter equaling 0. Then we have I less than 9, I++. Cool. So what it's going to do is it's going to start at 0. At the end of each loop, it's going to go up by 1, and the loop will keep going as long as the counter is less than some number. So this one is going to go, anybody want to guess? 9 times. Okay. 1 move, 2, 3, 4, 5, 6, 7, 8, 9. And then now, if we take a look here, oops, the end here, now I is equal to 9. Is this next move going to run? No, the loop is over because, as you might have learned in math class, 9 is not less than 9, because then you would have to decide which of these 9s is bigger, right? This isn't like shoe shopping where one store says it's a 9 and another store says it's a 9, and they're not the same number, or, you know, a 7 and a 7, whatever that number happens to be, where it's very, very different. Here, you know, in math, it's the number 9. It's always the number 9. So you can't specifically say which 9 is bigger. So cool. How could we change this so that he still does the same move, but going the opposite way? So here's what we're going to do. Instead, what we're going to do is, well, let's look. Okay, what if we just change the numbers, right? That's the easiest idea. Okay, so now, and we're going to flip this sign. So basically, if we start the counter at 9 instead of ending at 9, and we keep going as long as I is, well, what's the problem with this? If it's I less than 0, is 9 less than 0? No. So the loop isn't ever going to run, right? We want this, since we're going to be going down, we want to make sure our counter is bigger than 0. And then in place of plus plus, we'll do minus minus. So let's see what happens here. Okay. So we're starting at I equals 9. It runs and he moves. Now I is 8. It runs and it moves. 7. Okay. So now 6, he moves. 5, he's going to move. 4, he's going to move. 3, he's going to move. 2, he's going to move. So now I is 1, he moved. Okay. So now I is 0. Is 0 greater than 0? No? Cool. It's done. Okay, all you got to do is flip the numbers. So you can go up, you can count down, either way. So, cool, we just made him move 9 times. So now what if we wanted to make him go 2 spaces at a time? Well, we just add another move. So now let's take a look. Okay, so now I equals 9, that's our counter. So the loop is going to run because 9 is greater than 0. He does the first move, he does the second move. And now we go, and now I is 8. So he does the first move, he does the second move. 7, 6, 5, and now we can see, right? Now, what's going on here? We're at I equals 5, and he's going to run into the wall. So if you're going to do, say, like double up on the moves in your for loop, you're going to have to cut down on these. Okay? So what we might do is say, let's go back to going up, and let's try moving 4 times. Okay, because again, right, if you're going twice as, like, think about a giant and a dwarf, right, in, like, you know, some fantasy thing. If the dwarf wants to keep up with the dwarf is going to have to take, like, 10 times as many steps as the giant is, because the giant takes much bigger steps. It works the same way here. The more of that action that you're doing in the for loop, the fewer times you have to repeat it. So now we reset. We keep going. All right. So now I is 4. And he doesn't go. So he doesn't do that last one. Well, what if I really now just want to get him in that last space? Well, I got 2 options. I can either have him go through all that and then just make him move one more time at the end. Okay. Or I can do it before the loop runs. So he can move once, and then he's going to start moving 2 at a time. Cute. Nice. Now, let's say... Well, okay. Let me not get too complicated with it right now. In terms of, say, like, how could you count by 2s? Instead of going up by 1, let's say we wanted our counter for some reason to only be even numbers. Well, yeah, I think maybe I will not get into that right now just to not end up confusing you. So here we see in the next example something very similar to what I just did. We have some repeated action. So how do we know? Like, here's the big question. Put ball. Does that get repeated?